Hello, you have probably just finished chapter one and getting ready for a chapter one test. I will be going over the chapter test questions with you. It's a good way to review, to go over see what you need, what you already know, what you need to study. Chapter one has a lot of fundamental ideas, right? So it has a lot of concepts. It's very important. With vocabulary, you might want to, if you're having trouble with vocab, you might want to maybe do flashcards, read the chapter summaries, go through the sections. Definitely, I think the book, like if it has the bolded words, those are pretty important. I would maybe, go through and make sure, review those words, right? All right, number one, chapter one, name three collinear points. So collinear just means co is like together, linear is a line. So 3 points that are they line up, right? So there are multiple answers for this. So three collinear points. One could be points A, X, and C. So AX and C. You can also, here's AX and C. This is called a diagonal, right? And also DXB is also a possible answer, DX and B. It's only asking for one, so name three collinear points. Number two, name the intersection. Intersection is where two objects meet, right? So with this, it seems like a very simple question, but then this reviews like you need to know what this is. This is known as a ray. Ray CX, there is a direction. So ray CX, it starts at C and it goes in the direction of X. So ray CX, and it goes through A. So ray CX, it just goes on forever, ray CX, right? This is a line with double arrows. This is line AB. So line AB is down here. Let's answer the question first, right? So ray CX goes this way, line AB. They both share, intersection is the points that they have in common, right? For this, the intersection of a ray and a line, they don't have to intersect, but in this case, they do, right? So they intersect at point A. So their intersection would be at point A. With your ray CX, it does matter like XC and CX in terms of rays. They are different rays. So CX goes this way. XC would start at X and go the opposite directions through C, right? So be careful with rays. Lines doesn't matter. If you write like line AB or line BA, these notations, they are very specific. So line AB and line BA, they mean the same thing, right? But then with rays, you have to be extra careful. You also have line segments, right? And then you also, a big mistake that a lot of people have is they just write CX without anything. They just write like this. They'll just write CX, right? These notations. This refers to like the distance CX, right? When you have those symbols, this would be ray, this would be line, and then this would be a line segment with endpoints. So these notations, they do matter, right? And then one and two, they're asking for points. One was asking for points, so we put 3 points. Definitely put a comma in between. Like I've seen people just, these are AXC, right? That will actually mean something else. If you write like AX and you write something like AXC, this is going to refer to like a plane. So that's why when you want points, you want to say point A, point X, point C, right? All right, let's move on. Number three, which postulate justifies the statement AX? See how it's a distance AX plus distance XC is equal to the whole distance. This is a postulate. Remember, a postulate a postulate is an idea that doesn't need to be proven, right? We just kind of accept it. There isn't a proof for it. We use these postulates, we learn a few postulates, we use these postulates and other ideas in geometry like definitions, right? We use those together, properties of equality. We use all of those and then we prove other theorems, other ideas. So the big difference between postulates and theorems is postulates, you don't need to prove them, whereas theorems, there is a proof for them, right? And then after you prove a theorem, then you don't have to keep proving it over. You can use the theorem to prove other theorems as well. All right, so which postulate justifies this theorem? This would be a segment addition postulate. Segment addition. Definitely review segment addition postulate. Segment addition postulate. A key idea for segment addition postulate is the points have to be collinear. This point in the middle, x, it has to be on the segment. Like this, you can't have like, you wouldn't be able to say segment AX plus segment XB just because they have X there. AX plus XB would not equal to AB, right? So I think the common term was like between, like given a segment and a point that's in between these two endpoints, it has to be between, means that they are like they are collinear. The points are collinear. They're on the same line segment, right? X is not on line AB. So a common mistake is sometimes people will think like AX plus XB is AB. Well, that doesn't work because X isn't on AB. So we couldn't use that segment AB. So be careful with that. Number 4, if segment AC bisects BD, segment BD, name two congruent segments. Here's segment AC, here's segment BD over here. AC bisects BD. Bisects means to cut into two equal parts, two congruent parts. Bi, like bicycle, has two wheels. So bi is to cut into two. Bisects cut into two equal parts. Name two congruent segments. Congruent just means they're the same length, right? Or they're same length for segments, but you'll have congruent angles. You have other congruent figures. So congruent just means the same, right? If AC bisects BD, what's being bisected is BD. So BD is being cut into two equal parts. So for number 4, if AC bisects BD, AC is cutting BD into two equal parts, right? So AC cuts BD, bisects it. They both share, their intersection is X. That means DX is congruent. It's asking for congruent segments, is congruent to XB. And you put the segments, right? DX is congruent to XB. Common mistake on this one is people will say AX and XC, right? It doesn't say that BD bisects AC. It could be, but we don't know that. All we know is AC bisects BD, so BD is being bisected. So BD is the one being cut into two. Doesn't mean that, AC is being bisected, right? So be careful. AC bisect BD, DX is congruent to XB. Again, notation matters. If you look at the notation, this is the symbol for congruence. Segments are congruent. So let me just review like definition of congruent segments. By definition, congruent means this. I want to put double arrow because definitions are biconditional. Is it biconditional? It is biconditional. It goes both ways. So if two segments are congruent, their distances, their lengths are going to be equal, right? So these are just notation. So if two segments are congruent, it also means that their lengths are equal. What I mean is like if this was 4 units, if dx was 4 units, xb would be 4 units. So that's what this is referring to, numbers, right? Numbers, distances, measures, they're equal, right? Whereas the actual physical segments are congruent, meaning like we can move this dx on top of xb, we can translate it, we can move this and it'll fit directly on top, right? It's a perfect copy, right? All right, number 5, name the vertex and sides of angle 1. All right, 5, name the vertex and sides of angle 1. Here is angle 1. Other names for angle 1, you could call it angle, so if you have angle 1 here, it's also known as angle DXA, right? Also known as angle AXD, angle AXD. Sometimes I'll write the angle like this, right? Just so that it doesn't look like an L. So it's just personal preference. Sometimes like that, right? So angle 1 is also known as angle DXA and also angle AXD. You cannot call it angle X. A lot of times people will they just see angle 1 there, and then the vertex is that middle point right here. That's the vertex. So the vertex of an angle, because an angle is made up of 2 rays, right? So ray XD and ray XA, those are the sides of the angle, and the vertex is the point. So the vertex is the point of the angle. So the vertex is point X. We cannot call it angle X because that's not specific enough. If you if you tell someone angle X, right? If you just go off and you even like you tell a teacher angle X here, they won't know which angle you're talking about. There's lots of different angles that has X as the vertex, right? So that's why you can't call it angle X. Just like you can't call this angle A or angle B, angle C, or angle D, because there are multiple angles at that, right? You have XAB, you have DAB. So when you're calling angles, you want to be careful, right? You can call it angle 1. It's pretty clear that angle 1 is there. You just can't call it angle X. All right, so DXA, AXD. All right. 5. Number 6, name a right angle. So by naming a right angle, here's a right angle here, right? It tells you that's the symbol for right angle, that little box, that little square. So angle DAB would be a right angle, angle DAB. Or you can also call it angle BAD. Those are right angles, right? These are the same angles. Again, do not call it angle A because it's not clear that that is, it's not clear that we're just referring to that right angle as angle A. So angle DAB and angle BAD. Right angle has a measurement of 90 degrees. You might as well go through. An acute angle is less than 90, right? So like DAX and XAB, those would be acute angles because they add up to form 90. So they would each would be acute. You have obtuse angles, which are greater than 90. And then you have straight angles, which are like they form a line. So like angle AXC, that would be a straight angle. All right. Name 2 adjacent supplementary angles. 2 adjacent supplementary angles. Adjacent means right next to each other. They have to share a common side and vertex. So that makes it adjacent. Adjacent angles are angles that they share a common ray, right? And then supplementary just means they add up to 180 degrees. So 2 adjacent supplementary angles. So there are multiple answers here, adjacent supplementary angles. So I'm just gonna take AXC as our straight angle. AXC is made up of AXD and DXC, right? So you could say, name 2 adjacent supplementary angles. They're right next to each other. They share a common ray, ray XD. So you can say angle AXD and angle DXC, right? They form a linear pair. Adjacent supplementary angles, they form a linear pair. So linear pair. Depending on your teacher, right? They might tell you about linear pairs or not. It's not called that in this book, but in like newer books, there is a linear pair is a pair. They're a pair of angles, two angles that form a line, right? That are supplementary. They're actually adjacent supplementary angles. They form a linear pair. I'll bring this up because there's a linear pair postulate. Linear pair postulate just says that if 2 angles form a line, right, then they are supplementary. So that's what linear pair postulate says. All right, 7. Number 8, name 2 complementary angles. Complementary angles are angles that add up to 90. A common mistake is people will get supplementary and complementary mixed up. There are different ways to remember this, right? I've heard lots of different ideas where S is later, so 180 is greater, right? Whereas C comes before S, so that's why these 2 angles add up to 90, and then 180. You could think of it like that, or you can just remember complementary. They are right next to each other, well, adjacent. Complementary angles, they don't have to be right next to each other, they just have to add up to 90. For our purposes here, they just happen to be adjacent to each other since we're not given any measurements. But we do know that these 2 angles add up to 90 here. So name 2 complementary angles. Let's say this will be angle DAX and angle XAB. XAB. Again, you can name these angles like XAD or BAX as long as A is the vertex, right? Then you got that, right? So these are 2 complementary angles. And remember, you need 2. I've heard some people when name 2 complementary angles, they've told me like DAB, right? Well, DAB is 1 angle and it's 90. So they're getting the 90 idea right, but then two of them add up to 90, right? So it's not the whole thing. Yeah. So watch out for that. All right, number 9. Name the property that justifies the following statement. If AX is congruent to XC and XC is congruent to XD, then AX is congruent to XD. This is known as the transitive property of congruent segments. Transitive property. So 9 would be transitive property of congruent segments. You also have transitive property of congruent angles, right? You have lots of, the three main ideas is reflexive property, symmetric property, and here's transitive property. So those were like the three main ones, right? You also have property of equality, where the difference is like instead of congruence, it's just equal signs, right? If A is equal to B and B is equal to C, then A is equal to C. That's transitive, where you have that bridge. So definitely review your properties. It looks like there's a lot of them to review, but it's congruence and equality. The only difference is that symbol in the middle. One's talking about congruence, the actual segments or the angles. The other one's talking about like numbers or distances, right? Or measures with equality, all right? 10. Complete if X is the midpoint of AC. So from this diagram up here, if X is the midpoint, so just know that midpoint, it's a point that's in the middle, right? X is the midpoint of AC, then AX is equal to half of what? So this would be a definition, right? Definition, I think it's a definition. I'll have to recheck because there is one that's the definition of midpoint, and then there's also the midpoint theorem. I want to say it's the definition where if X is the midpoint of AC, then AX is equal to half of AC. AX is this part, is half of the whole. So you want to say 10 AX is equal to half of AC. And this is talking about the distances, the numbers. So it's not talking about like, it's not, sometimes people will put like segments on top, right? This is talking about like if AX is 5, then if AX is 5 and this is a midpoint, AC would have to be 10, right? So what was I was trying to explain like the difference between the definition. So definition of midpoint is a midpoint that cuts it into two equal parts. This is the theorem. Definition cuts it into two equal parts, meaning by definition, all right. So definition of midpoint is a point on a segment that cuts the segment into two equal parts. So if X is the midpoint of AC, by definition, we can say AX is equal to XC. That would be definition of midpoint. Yeah. I had to like rethink and like go through the definition and read it out. So then this would be midpoint theorem. So midpoint theorem is the way I remember the difference between definition of midpoint and midpoint theorem. Midpoint is, I remember the definition of midpoint, which is to like, it's a point that divides a segment into two equal parts. So this would be my two equal parts. The theorem deals with the whole segment. So when you have midpoint theorem, it will say like, you're dealing with one part is equal to the half of the whole, right? Or sometimes it'll say like two of AXs will equal to one AC. So if the statement has to do with the whole segment, then it's the theorem. If it's just dealing with equal parts equal to each other, then it's just definition of midpoint. It's a little tiny, I mean, I feel like I'm being really nitpicky. The idea is really simple, right? But to remember the difference between definition of midpoint and midpoint theorem, that comes in like when we're trying to talk about proofs and you're trying to like, you're trying to prove something. So you want to use the right statements to prove them, right? So knowing the difference between the theorem, because we can prove the theorem again, right? We can prove midpoint theorem. So you should have done that before, but I don't know, right? Well, it might come up later if you haven't done it yet, but that is number 10. So AX is equal to XC. I know this is taking longer because I'm also trying to give you a review of chapter 1, so I'm trying to go over like what I remember about it. So, but then actually doing it, if X is the midpoint of AC, AX is half of AC. All right. All right. Let's see. Next. Okay, number 11. If measure angle 1 over here is 46, find measure angle DXC and find measure angle CXB. All right. So number 11, if measure angle 1 is 46, measure angle 1 equals 46 degrees. We know that measure angle 1 plus measure angle DXC, they form a linear pair, right? It's a straight angle right here. They form a linear pair, so they are supplementary, meaning they add up to 180 degrees. So you would just find the supplement of 46 to find measure angle DXC. Right, you subtract 46 from both sides, measure angle DXC should be 134, right? 46, yeah. So that's DXC. And then to find CXB, which is this over here, CXB, these two angles, they're vertical angles. So you have a vertical angles theorem that says vertical angles are congruent. So you know that CXB, measure angle CXB, should equal to 46 degrees as well. If you didn't use vertical angles theorem, how these angle 1 and angle CXB are related, you can also, the proof for it is to know that these form a straight angle, they're supplementary. These two form a straight angle, they're supplementary as well. If these two angles have to add up to 180, these two angles have to add up to 180. Since they both contain CXD, these two angles have to be the same, right? All right, number 11. Number 12, if measure angle DAX is 70, so DAX is here, this is 70, find the measure of XAB. These two angles, they are complementary, DAX and XAB. So DAX is here, this is 70, right? So XAB, so we want to write measure angle DAX plus measure angle XAB. They are complementary, meaning they add up to 90 degrees. Since DAX is 70 degrees here, plus measure angle XAB is equal to 90 degrees, the complement, you subtract 70 from both sides. That means XAB has to be 20 degrees. All right. On a number line, 13, on a number line, J has coordinate -7, K has coordinate -2, K is the midpoint of J, segment JL, find the coordinate of L. So each point, ruler postulate says that each point you can assign a value, right? Their coordinate, and in between those values, you can find a length, right? So first, for these type of problems, you want to draw it out. I would draw them up. So number 13, on a number line, J has coordinate of -7. So let's have our little number line here, right? We will just, J is -7, all right? So J will be -7, this is J. And then K is -2. So let's, 1, 2, 3, 4, 6. You really don't have to mark off all of these, right? It's just that, since I have grid graph paper, it's easier for me to do that. So -7, 6, 5, 4, 3, 2. This will be -2. That is, K has coordinate -2. So at K right here, this is -2. K is the midpoint of JL. So since K is the midpoint of JL, L is going to be somewhere to the right. L is somewhere over here. So L is somewhere over here, right? We know that K is the midpoint, meaning K is in the middle. So this is in the middle. At a certain number of distance, that's where L is going to be, right? So this is just one way to do this, right? Find the coordinate of L. So to find out where L is, what you can do is, how long is JK, right? Remember the distance is always the difference. From -7 to -2 will be 5 units. So if we do this visually, we know that this is 5 units. 5 units from here, we can say that L is going to be 5 units from -2 should be at 3, right? From -7 to -2 is 5 units. 5 units, 2 units would be 0. And then we have 3 left over, so L should be right here. So L, the coordinate for L is 3. The distance between J and K is 5. Let's say if you don't want to do it visually, graphically, right? You can say the distance between J and K, it's the absolute value of the difference. It doesn't matter if you do -7 minus -2, or you can say -2 minus -7. When you take the absolute value, is the distance, is the positive distance, right? So this would be +2. So this absolute value of -5, or this is a +7, absolute value of 5, it's 5 units. So since JK is 5 units, we can add 5 units to -2 to find K. KL has to be 5 as well, right? So you could algebraically, you could say KL is equal to -2 plus X, right? Which is also equal to 5. -2, is that right? Oh, not plus X. Remember, it's the difference. Yeah, watch out for these little mistakes, right? Remember, it's the difference. So that's why it's minus. So you said -2 minus X is equal to 5. Or remember, you can have like, you can always say -2 minus X is equal to -5, right? And we'll do both cases just for fun, just to see where this takes us. This is calling L X, right? If L was X, this would be -X. You add 2. If you add 2 to this, oh, I see what we're doing. If we add 2 to this, you would get +7 multiplied by -1. It would be -7. This is not actually KL. Well, KL is 5, but then this gives you the coordinate of J, right? Because remember how J right here, J J right here is for this -7. This is why back in algebra 1 we had, how to solve absolute value equations, right? And then for this case, this is saying like finding the points away from -2 right here. This is the center point. You can go 5 this way, which will give you -7. You can also go 5 this way, which will give you the other answer, right? So -X equals, you add 2, which will be -3. X will be +3, which is what we want over here, right? So this is seeing it algebraically, right? A little review with absolute value where K is the midpoint. There are also other methods with the midpoint equation, but then we will get that like in second semester when we do coordinate geometry. But visually, that's why we want to draw them, because sometimes when you do it visually, you can see it. It's quicker too. So -2 here's 5, and then you go 5, you end up at 3. If you do it algebraically, you got to remember, you're asking like 5 units from a center point of -2, right? So 5 units away from the center point of -2, to the left would be -7, to the right would be +3, right? Just a little algebra review, okay? All right, 14, continue. 14, complete with always, sometimes, or never, 14 and 15. So these are the conceptual problems, right? So let's see. 14 says, if 2 planes intersect, then their intersection is sometimes, always, or never a segment. This is like, if you think it's always, that means you can't find a counterexample where it's something else. Same thing with never. If it never happens, you can't think of a case where it will happen. Sometimes is when you can think of it, when you can think of and examples for this that happens, both times, right? You can think when it happens and when it doesn't happen. So if 2 planes intersect, then their intersection is this one should be never, right? So number 14 should be never, because the planes have to intersect. If they intersect, it's not going to be a segment. It's going to be a line. Two planes intersect in a line. Two planes intersect in a line. It's never going to be a segment because planes, it's like a flat surface that goes on forever. So their intersection will go on forever too. Let me try to draw how I draw intersecting planes. Oh, let's do a horizontal and vertical plane. So what I try to imagine is I'll draw a vertical plane like this, right? Their intersection is a line. And then there. It's never just this segment. And then you could use dotted lines. So their intersection would be this part right here. I draw a vertical plane and then I try to imagine, this is where they cross, right? And then their intersection is like the points that they share. It's never going to be a segment because planes go on forever. So the intersecting, it's going to be like a line, right? Think of like your walls in a room, right? You see a segment, but then a plane keeps on going. So that corner where the two walls meet, it will always extend. So that's why it becomes a line. That's why this is never. Be careful with these problems because it sets you up. It says if two planes intersect, right? So it already says that the planes intersect. So if they intersect, never a segment, always going to be a line. So sometimes the tricky part with these problems, it'll just say your statement could be two planes intersect, two planes always, sometimes, or never intersect in a line, right? So then if that was the question, you have to the planes could intersect or they don't intersect. So that's why um, you have to watch out for the wording of some of the problems, right? So they kind of set it up to say that they do intersect. So if they intersect, it's never a segment, it's always a line, right? All right. I guess the question would be two planes intersect sometimes, always, or never in a line. If it doesn't say that the planes intersect, that would be sometimes because it could be two planes that don't intersect, right? So if it doesn't tell you that the planes intersect, you can say two planes always, sometimes, or never intersect in a line, right? All right, number 15. A line and a point not on the line are sometimes, always, or never coplanar. A line and a point not on the line. So if we draw this out, 15, a line and a point not on the line, right? Are they always, sometimes, or never coplanar? So coplanar just means they're on the same plane. Uniquely one plane, right? They're on one, are they on the same plane? So this one is actually trying to test the 14 and 15. It's testing whether you remember those postulates, those line postulates, point lines and plane postulates, right? They're all ideas. So this one comes from, this would be, let me think, they will always be coplanar. So I'm going to say it's always. Because to define a plane, you just need 3 points to define a plane, right? This line, you need 2 points, at least 2 points to define a line, a unique line, right? If you only had 1 point, many lines go through that 1 point. If you only have 1 point, many lines go through it. But if you have a unique line, a unique line, you have 2 points. So minimum of 2 points, it will define uniquely one line that goes through it. So since this line gives you at least 2 points, you have a point that's not on the line right here. These 3 points, they will define uniquely one plane, right? Technically you could have a line. Let me review something. You could have a line like this of many planes go through this line, right? Because even though these 3 points are collinear, you can have an infinite amount of planes that go through these 3 points. It could be flat, it could be coming out at you. So that when they say not on the line, they are always going to be coplanar. A line and a point not on the line are always coplanar. So it's this case over here. I was just bringing up other cases. Just be careful, those words do matter, like whether their points are collinear or not. Always do a drawing and try to figure out like, be, what do I want to say? Be familiar with the ideas, or like, 2 points or one line. Yeah. All right, 16. 16. Let's see. If ray RT, so it's referring to this figure right here. If ray RT bisects an angle, so an angle bisector, it bisects an angle URS, so URS over here. Measure angle 1 is 6x minus 30. Measure angle URS right here is 5x plus 24. Find the value of x. Awesome. All right. So 16, if you can, I would always try to redraw, right? And on tests, if it's allowed, I would also mark up your tests, because that sometimes marking it helps, right? So here's T, here's S. Let's go angle 3, 4, 1, and 2, right? So let's always mark off what the information that they give you. So if it says like ray RT, remember ray starts off at R, goes through T like that. It bisects angle URS, which is this angle right here, URS. That means if it bisects, it cuts URS into 2 equal parts. So these two are congruent, right? Since measure angle 1 equals 6x minus 30, we know that measure angle 2 is equal to that, so that's also going to be 6x minus 30. And then it says measure angle URS is 5x plus 24. URS is, measure angle URS is equal to 5x plus 24. So when we add these two, it should equal to this. That's one way to do it. Like, you can say there's different ways to explain this. There's different ways to look at it. Some you might want to use angle addition theorem, right? Angle bisector theorem. Angle bisector theorem, not angle addition theorem. Angle bisector theorem, we use angle addition postulate to prove angle bisector theorem. Angle bisector theorem says 2 measure angle 1s equals 2 measure angle URS. 2 halves make the whole thing. 2 of the smaller ones equal the whole thing. To prove this theorem, it actually comes from angle addition postulate. So angle addition postulate says measure angle 1 plus measure angle 2 equals measure angle URS, right? But since measure angle 1 and measure angle 2 are equal, that's how we come up with 2 measure angle 1s, right? So whichever way you want to do it, you would substitute then, right? I'm just going to substitute into the bottom one since I wrote it out here. If you didn't write out measure angle 2, then you'd probably do this over here. Like, with doubling 6x minus 30 is the same as adding 6x minus 30 plus 6x minus 30. All right, let's do that. So 6x minus 30 plus 6x minus 30 equals 5x plus 24. So 12x minus 60 equals 5x plus 24. Minus 5x from both sides, you get 7x minus 60 equals 24. Add 60 to both sides, 7x equals 60, 84. And then x is equal to 84 divided by 7, 84 divided by 7, 1, 12, right? So it's equal to 12. X equals 12. And number 16, it says find the value of x. There's the value of x. Always pay attention to the question, because sometimes they'll ask what's the measure of URS, or what's measure angle 1, what's measure angle 2. So depending on the question, sometimes people, they just rush through it and they don't answer the question. This one's just asking x is 12 and we're done, right? If it's asking what's angle URS or what's measure angle 1, you just substitute it back in and check. If you do have time, a good thing to do is always to go back, like take your answers and go back take whatever you get for x, go plug it back in and make sure that everything fits, right? That's a good way to check. That's if you have time. If you don't have time, then move on, try to answer other problems, right? And then if there's time left over, come back and then double check, right? I wouldn't spend too much time on any one problem. I would always like on tests and quizzes, I would always try to go through, do all the ones that you can do quickly first, right? That you understand, and then go back and try the ones that might be giving you trouble. You don't want to spend too much time on a problem that you're having trouble with and then not do the problems that you could answer, right? So that's just something I would look out for. All right, 17, justify each statement. This is like, justifying the statement is like finding the reason. Why is this true, right? So let's look at 17. It says justify statement, measure angle 1 plus measure angle 2, 1 and angle 2 is equal to URS. That is just angle addition postulate. The sum of the smaller parts equals the whole, right? It has nothing to do with angle bisector or anything. It's not saying 1 and 2 are equal. 1 and 2 don't have to be equal. As long as you add the 2 up, they equal to the whole. So the first one, that is just angle addition. Angle addition postulate. And advice about proofs and asking for reasons, you're always asking why. Why is this true? Why do I know this, right? There we go. And then a lot of these postulates and theorems, they have names just to make it easier so we don't have to always rewrite out the whole idea, right? All right, letter B, if RT equals ST, RT is equal to ST, then 1/3 RT equals 1/3 ST. So this is a property of equality. You see how it remains equal here? You're saying like if you're given RT, how is it changing? You are multiplying both sides by 1/3. So I would say this is a multiplicative property of equality. Equality. We are multiplying both sides by 1/3. If you multiply RT by some number, ST by some number, they will still remain equal, right? Sometimes people can argue that it's division because the inverse of multiplication is division. So if you had like RT over 3 equals ST over 3, well, multiplying by 1/3 is the same as dividing by 3. Remember division? When you're dividing, you're multiplying by the reciprocal. So if you're dividing by 3, that's the same as multiplying by 1/3. Usually you might see some people saying that this is division property of equality because you're dividing both sides by 3, right? Which is the same as multiplying both sides by 1/3, right? I initially said this was multiplying by 1/3. I still say that because that's what we're seeing here. But if it was written like this, then I would probably say, if it was written like this right here, I would probably say division property of equality. Division property of equality, right? So it depends what you're doing to both sides of the equation. All right, C. If line RU is perpendicular to line QS, line RU is perpendicular to line QS, then URQ is congruent to angle URS. All right. This one has to do with like theorems that we had, right? From your previous section. So this one is saying like, when you have perpendicular lines, the adjacent angles form, they will be congruent. So if you have a perpendicular, there are like, I think a few of these perpendicular line theorems, right? There isn't a name for them. So you would have to like definitely look through like the chapter review and also the section that would, the summary, right? There's a lot of postulates. There's a lot of ideas. So let me write this one out. So this one is saying adjacent angles because URQ and URS, they're adjacent angles. So adjacent angles formed by perpendicular lines are congruent. Adjacent angles formed by perpendicular lines are congruent. You can prove this because by definition of perpendicular, you have a right angle. These two angles, they form a linear pair, so they're supplementary. So if this is 90, this will also be 90, right? Since both angles are 90, then they're congruent to each other. So there are ways to prove these statements. But to justify it, you don't, if there is like a theorem that you can use, you might as well you use a theorem. You don't have to always reprove the theorems. A lot of times, a lot of students like to keep reproving theorems, then that's why like, it takes them longer to do things, right? Plus, there's also, you're building on top of your ideas, right? You want to like, if you have a new theorem, you want to learn the theorem, it's to make life easier for you. All right. 18, write a two-column proof. Angle 2 and angle 4 are supplementary angles, meaning they add up to 180. We want to prove that angle 2 is congruent to angle 3. All right. With proofs, there are a lot of different ways to do this, right? We're actually congruent supplements there. The hard part is figuring out whether you've had this theorem yet. If you had the theorem, then you can just use the theorem to prove it, right? Let's see. I think you have had the theorem. Yes, congruent supplements theorem. It's theorem 1-7. If you look at theorem 1-7, you don't really like, for me, I don't have my, like, you don't want to memorize the numbers of your theorems because the numbers don't really mean anything, but it's more of the idea, right? But let's go through this proof together, right? So number 18, again, I want to copy it over. Well, we'll just redraw it. All right, let me stop recording so you guys don't have to like watch me draw this. All right, with magic, there's the drawing, right? How I go about doing proofs is I like to mark them up, right, and see like trying to have a plan for it. We're trying to prove, and you will have more practice with this. Don't worry if like a lot of times people freak out over proofs, right? They're not sure how it works. It's like a new game with different rules, right? Two-column proof is on the left side you have like your statements. On the right side you have your reasons, right? You have your given and also what you need to prove, given information. All right, so let's say given angle 2 and angle 4 are supplementary angles. You're trying to prove that angle 2 is congruent to angle 3, right? So you're trying to prove this. Are these two congruent, right? You're given that 2 and 4 are supplementary. So what I like to do is I like to write down different notes, right? What does the given tell me? 2 and 4 are supplementary. It means that they add up to like 180, right? These are supplementary. But then what do I know? Since I have 2 and 4, and then I want to prove 2 and 3, it'd be nice if I could say something about 3 and 4. 3 and 4, they form a linear pair. So angle 3 and angle 4 form a linear pair. And that's from the diagram. Like the diagram, you have line QS, right? So this is a straight angle here. So that means I think the textbook uses angle addition postulate. It's a special case in angle addition of a straight angle, right? They're supplementary, so linear pair postulate would probably fall under that. So this, if you've been going straight by the book and not having like new vocab or anything such as linear pair postulate, they would say that that step would be like angle addition postulate. I'm going to use linear pair postulate. 3 and 4, they form a linear pair. It says that they are supplementary. So since we have 3 and 4 are supplementary, 2 and 4 are supplementary, we have a theorem, congruent supplements theorem. If two angles are supplementary to the same angle or two congruent angles, then the two angles are congruent. So if we look at this, if two angles, 2 and 3, if they're both supplementary to the same angle, angle 4, then these two angles will be congruent. I'm going to use the theorem because then I don't have to like reprove it. It's an easy theorem to reprove. It just makes your proof super long, right? So we can always talk about it. We'll talk about it while I'm writing it out, but that's pretty much the plan of the proof. I look at like what I'm trying to prove, 2 and 3 over here. I know, and then also what do I know? I know 2 and 4 are supplementary. I know that 3 and 4 are supplementary, right? And now to write it out, which is a part where a lot of people have trouble with. And it's because like you haven't had a lot of practice. The more practice you had, the more exposure you've had to seeing how these proofs work, you should be able to pick it up, right? But the problem with proofs is the catch is you have to do them. If you don't do them, you can't just look at them and then you got it, right? It's like riding a bicycle. You can't just watch someone ride a bicycle and then all of us, if without you actually getting on and riding, you can't just watch it and then all of a sudden you can do it, right? It's a lot of things in life. You really have to just sit down and do them. All right, so um, all right, so we have our statements, and we have our reasons, which is what we justify, right? So I'm not gonna put the given first because it's a habit that a lot of people like to do. They like to just put the given. Later on, you're gonna have some proofs where you're not gonna have to use all the given, right? So that's why, and sometimes you're given a lot of things that they like to put all the givens all up front, but I like to put the givens in when I'm going to use them. So, but with introductory, I'm going to purposely not put the given up front just to show you that you don't have to, right? Because then what happens is people start thinking like, oh, we put the given up front, and they just always keep putting the given there, and they're not really thinking about it. They're just like going through the motion, right? What you want to do is you really want to think about this. All right, so first one, I'm going to put angle 3 is supplementary to angle 4. Number 2, and then with proofs, you're always asking why for each step. We'll go through the whys afterwards, right? We'll talk through it. Angle 3 is supplementary to angle 4. It's because they form a linear pair. Linear pair postulate lets you do that. Then we also know that angle 2 and, angle 2 and angle 4 are supplementary angles, right? And that's given. 3, if two angles, 2 and 3, are supplementary to congruent angles, right? Then they will be supplementary to each other. That's our theorem. Congruent. There is a name for it. It's called congruent supplements theorem. I don't think this book gives a name for it, but you can always write it out, right? You can always write out the idea. That always works. Let's see. So angle 2 is congruent to angle 3. All right. Let's go through this. So 1, angle 3 is congruent to angle 3 is supplementary to angle 4. They form a linear pair. This is linear pair postulate. In your textbook, I think they've said it was angle addition. It's part of angle addition postulate. You can go over and like review that, right? Angle addition postulate is really, it's a general case. Any larger angle made up of its smaller angles, two smaller angles, as long as they have a shared common side, common ray. Linear pair postulate falls under that. It's a special case where the angle is a straight angle, right? And linear pair postulate says that if two angles form a linear pair, two angles that form a line, then they are supplementary. And that's what we're saying. We're saying they're supplementary. Step 2 is given. We are given this right here. Sometimes when you look at a statement and you don't know why it's true, always check the given. Step 3 is congruent supplements theorem. There. This is a theorem because it can be proven, and we should have gone through the proof in class, right? Hopefully. If we don't have the name, you can always summarize it. If two angles are supplementary to congruent angles or the same angle, right? In this case, it's the same angle or the same angle, then the two angles are congruent. The proof is very easy. I'll talk through the proof, right? Just to like jog your memory. You can say like 3 and 4. Definition of supplementary means 3 and 4. We'll write it out here. Like angle 3, measure angle 3 plus measure angle 4 equals 180. That's definition of supplementary angles. Step 2, since you were given their supplementary, definition of supplementary again, measure angle 2 plus measure angle 4 is equal to 180, right? Because definition of supplementary for 1 and 2, they're both equal to 180. Since they're both equal to 180, they're equal to each other. So you can use substitution or transitive property. If you're dealing this as a whole, think of this as A. If A is equal to B and B is equal to C, then A is equal to C, right? If two sides are equal to the same thing, they're going to be equal to each other. So you could use like transitive property of equality, or transitive is just a special type of substitution as well. So you could say measure angle 3 plus measure angle 4 equals measure angle 2 plus measure angle 4. Last step, you could subtract, oops, sorry about that. You could subtract measure angle 4 from both sides. Then you get 2 and 3 the same. And by definition of congruent angles, if the measure of two angles are equal, then their angles are congruent. See how like this would make the whole proof pretty long, right? If you don't use the theorem, you'd go through and reprove it, which is okay. I mean, that's okay, right? It's okay. It's just more time consuming. And chances are you probably have done this already to prove this theorem. So once you've proven a theorem, you can always use it in your future proofs. All right. I hope this helps. Sorry if I rushed through things, but you can always go back and email your teachers, right? You can always contact me if you want, if you have questions, if you need more, if I sped through something and you didn't get it. Definitely ask your teachers questions. Always ask questions, right? And good luck on your test if you are studying for it. All right, I hope you're studying for it. And don't just study this. I mean, you should always, whenever you're doing your homework, that's already you're starting to study already, right? You're starting to practice. Like go over homework, go over notes, practice problems. If you want fresh new problems, I always try to recommend like Khan Academy, right? They'll have like different types of problems, test these ideas. You don't want to, a common pitfall is people memorize how to do one type of problem, but it's the concepts that's important. Sometimes you change the wording of a problem, it's still the same concepts. So as long as you understand the concepts, you should be able to apply it. You don't want to memorize how to do a problem. You want to understand the idea behind it, right? And you want to practice it as well. All right, good luck and good luck. All right. It's